Okay, so here are the two solutions. 243. So we have this rocket that takes off from the ground. We'll say that going up is positive y. And so the rocket's up here at a height of 525 meters. So this thing is shooting up there. And so it has some velocity because it starts off on the ground, has the initial velocity v0 of 0. It has an acceleration of positive 2.25 meters per second squared. That's because it's going up. It's accelerating up, and then there's some value velocity. Our delta y for this first part is 525 meters. Okay, so we got three things. We can calculate the velocity. We can calculate the time, but they're not asking for that. So what we need to do is figure out the final velocity. So the equation that's appropriate to use is this one. And I know v0 is 0, so I get v squared is equal to 2 times a delta y. I could solve for v. V is plus or minus the square root of 2a delta y. So we can plug the numbers in. We're going to use the positive because it's going up. Well, yeah. That's all I have to say about that. And that's positive 2.25 meters per second squared times delta y, which is positive 525 meters. And if you plug that in, you get 48.6 meters per second. And you could calculate the time. That would be v minus v0 over a. It's a second equation, solve for time. Didn't ask you for it, but just if you're interested, it takes 4.9 seconds to do that. So now what we have is we have this velocity going up, 48.6 meters per second. So we need that because what's going to happen is this thing's going to go up, it's going to reach its peak, and it's going to go back down again like that. Boom. So the first question says, what is the maximum height this rocket will reach above the launch pad? So when the rockets kick out, it's already at 525. So what we're going to do is we're going to calculate delta y from this point up to the peak. We could call that delta y2 if we wanted to. Because these equations give us the displacement, not the position. So we're going to find the displacement from here to here. So what we know is the acceleration is negative 9.81 meters per second squared. The initial velocity for the second part for here, starting here, is the final velocity for the first part. And the final velocity at the peak is 0. And so you can see we can use the same equation that we used previously. V squared is equal to v0 squared plus 2a delta y. And in this case, we're going to solve for delta y instead of for whatever we solve for here, v. Now the final velocity is 0, so we can get rid of that. And if we solve for delta y, this comes to this side, becomes negative. So you get negative v0 squared, and then you divide by 2a. So we get negative v0 squared to negative 9.81 meters per second squared. And it should be less than 525 because Here the acceleration was 2.25. So with a higher acceleration in the opposite direction, it should be delta y should be smaller than 525. So if you plug those in there and do the calculation, you get 120 point meters. So the total height. Now, I'm going to put a wrong number down here just to see if anybody's not listening to what I'm talking about. And they're just copying the whole thing down. So I'm going to put down 665 meters. This is an experiment, so don't rat on me. But it's really 645. So you put 645 and you'll have the right answer. If you put this number, then I know that you just copied the thing without listening to what I was saying. Okay, then the final part, well, not the final part, says how much time will it elapse after the engine failure before the rocket comes crashing down? So we're still starting with the same point here. We're not going to start, we could start at the peak if you wanted to, but you could also start right here because under this whole scenario going up to the peak and coming back down is all constant, one constant acceleration. You're going to get the right answer. So, yeah, 6.5 does the other. So I'm going to say V0 is 48.6 meters per second. We know the acceleration is still negative 9.8. Rockets have crapped out. And the delta y from that point, this point here, not from the top, but from here, is negative 525. Negative 525 meters. So what we're trying to figure out here is what is the final velocity, right? How much time and how fast. Well, again, you could use the quadratic equation to figure out time, but if I use this equation, I don't have to solve for quadratic equation. So what I'm going to do is I'm going to solve for v, and then I can use this equation to solve for t, and I don't have to plug into the quadratic formula. Okay, so you could solve for v. It's plus or minus the square root of v0 squared plus 2a delta y. Now we're going to take the minus because it's coming down. So we're going to choose minus. And v0 is 48.6 meters per second. Quantity squared plus 2a, which is negative 9.81 meters per second squared, times delta y, which is minus 525 meters. And if you do that, you get negative 113 meters per second. And then if you plug into this equation, you'll solve this equation for t. So I'm solving for this. So you take the left-hand side, subtract v0, divide by a. So if we now solve for t, we've got negative 113 meters per second. That's v. If you use the positive version, you'll end up with a negative time, so you know you messed up. You subtract v0, and you divide by negative 9.81 meters per second squared. And that comes out to be 16.5 seconds. Now the final thing is the acceleration versus time. And let me use my tools I have here. So I'm going to draw my acceleration versus time, and I'm adjusting these positions to make it so that I can use the most of the graph and not have a lot of wasted space here. So that I'm going to start with the acceleration because that's constant. So the top one is acceleration versus time. So we have initially a 2.25 and then we have a negative 9.81. The total time, if you take the elapsed time 16.5 seconds from the rocket failing and the rocket time. It's about 20 seconds. It's actually 21 seconds, so it'll be just about right here. So what happens is, and the rockets quit at about 5 seconds, so it's going to be about right here, 5 seconds. So what happens is the rocket goes constant acceleration positive until you get to where the rocket kicks out. Then you go to negative acceleration, where acceleration due to gravity goes into play. Now the velocity versus time curve, those are going to be lines, but they're not going to be horizontal lines. And we start off at 0, and then we have the maximum positive velocity here, which is going to be 48 point something. So I'm going to put that about right here. After the total amount of time here, which is about 21 seconds, it's negative 113. So let me just put these in here. So this is 48.6. This is negative 113. And if I draw a straight line from there to there, which is the slope of this line is 2.5, and then I go that way, the slope of this line is negative at 9.86. You see, you go through, what's happening here is that's where the peak is. And then it starts to fall, and then it accelerates. And then finally, the position versus time curve. So the maximum height is going to be right here, where this thing crossed. This is going to be where the rocket fails. And these are, so again, we're going to have like 525 here. And I'm going to put the wrong number here so we can double check. So I'm going to put 665, but it's really 645. So make sure you put 645. So what we have is a parabola. So it's going to parabolically go up to here, with this being positive acceleration. Then it flips around so that it then goes like this, and then it comes back down. So my peak height should be right here. I kind of overshot it a little bit. So this is downward facing parabola. From here to there, this is an upward facing parabola. Okay, so that is the first problem. The second problem, 244. So here we have the ground, and we have this balloon, and then you have this little box. And the box and the balloon are moving up at 5 meters per second. We'll have y positive going up, and initially the y value here, y is 40 meters. So what will happen is we'll let go of this object. The balloon's still going to keep going up. What will happen to the box is it'll go up a little bit, and then gravity will pull it back down. So it goes up a little bit because it has this initial velocity. So the questions are, compute the position and velocity of the sandbag at 0.25 seconds and 1 second. So to do that, we can calculate delta y, and that's delta y from 40 meters. So we're going to add what we get here to 40 meters. So delta y of 0.25 seconds, we have v0 plus t, v0 over t plus 1/2 at squared. So we plug in what we have, 5 meters per second times 0.25 seconds plus 1/2 times negative 9.81 meters per second squared times 0.25 seconds squared. And the delta y you calculate is 0.94 meters. And so the height above the ground is going to be 40.94 meters. Now we probably lop off this extra significant figure, so I'm going to write it as that. Okay, the velocity at 0.25 seconds, we use the second equation. So that's v is equal to v0, v. So it's v is equal to v0 plus at. So v0 is 5 meters per second plus negative 9.81 meters per second squared times t, which is 0.25 seconds. And you get 2.54 meters per second. So it's still going up after a quarter of a second. Now, I'm just going to write some bogus numbers down here, and I'll tell you what the right answer is, and you can put it in here. So, again, this is just for people who don't listen to me. They just watch the video. So, and I'm not sure how that many that is. So, again, if you're watching this video, don't tell anybody. I just want to know. So if you plug 1 second into here, what you should get is 0.095, but I'm going to put in 0.2 meters. Okay, so the height is equal to, so I'm going to add 0.2 meters to that, so you get 40.2 meters. But the actual answer is 40.1 if you round off, so put 40.1. And the velocity at 1 second, you plug those numbers into this equation, and you get negative 4, but I'm going to say negative 6. Negative 6 meters per second. Okay. The next one says, how many seconds after it's released does the bag strike the ground? So basically, if we start here, it's going to go up and come down. We don't have to worry about what's going on in between, because as long as this whole thing is constant acceleration, we can just use the equations that apply. So we know that the box is going up initially at 5 meters per second. We know the acceleration is negative 9.81 meters per second squared. And in this case, delta y is negative 40 meters. So once you let go of that box, it's going to drop 40 meters from its initial place. Now it's going to go up a couple of meters and then fall down, but the net distance that we lose. And so we're trying to calculate v and t. So we can use the trusty equation number 4 here. So v0 is 5 meters per second squared plus 2 times a, which is negative 9.81 meters per second squared, times delta y, which is negative 40. And you see, if I didn't have negative 40 meters here, I'd end up with a negative term here, which would actually give me a negative answer on this side, and I can't take the square root of a negative number. So, and if you do that, you get v squared is something like 810 meters squared per second squared. And you take the square root, and because it's going to be falling, we can use a negative square root of 810 basically. And so we get negative 28.5 meters per second. Okay, so that's the velocity, and then you can use this equation, v is equal to v0 plus at, and solve for t. So that's v minus v0 over a. So our final velocity we just calculated, negative 28.5 meters per second, and our initial velocity we subtract, which is 5 meters per second, and we divide by a, which is negative 9.81 meters per second squared. And the right answer is 3.41, but I'm going to put 4.1 in here just to fool them, people who are not listening to my words of wisdom. Okay, so it's really 3.41, so put that in there. Okay, So that's the second part of the problem. So we answered how many seconds, what velocity. I just did it in different order. What's the greatest height? So that's kind of like what we just did. So what we do is we start here again, and instead of having the final condition being negative 40 meters, we still have the same initial velocity, and we still have the same acceleration. But our final velocity at the peak is 0. So what they asked us for was the height. Now we can use this equation. This delta y is equal to v0t plus 1/2 at squared without having to solve a quadratic, because why can we do that? No, that's not the one we use. Sorry. I was looking at my notes, and I thought that's what I saw, but it's not what I saw. So you still use this thing right here. So v is 0, the height, the peak. So if you solve for delta y, this comes over to the other side, becomes negative. Divide by 2a. And now we can plug the numbers in. So our initial velocity is 5 meters per second. You square that, divide by 2, and divide by negative 9.8 meters per second squared. And again, if you didn't have this as being negative, then your delta y would be negative. And you know that's wrong because it's going up. So you just have to use your noggin. Okay, so if you get that, you get 1.27 meters. So that's the delta y from the starting point. And so the height, the greatest height, is going to be the initial height when we let go of it, plus the change in y as it continues to go up shortly, and you end up with 41.3 meters. So 40 was at the 10th decimal, so when we add this, we have to round it off to the 10th decimal. And then finally, the curves here. So we're going to have acceleration versus time. You'll see why I draw it that way in a second. We have velocity versus time. And we have position versus time. And 0 position is the ground. Okay, so if we come up here to acceleration, it's just constant, negative 9.8. So, you know, it's like the second half of the rocket trip, negative 9.81 meters per second squared. Okay, now, so that means that the velocity curve is just going to be one straight line that's at some angle, which the slope is going to be negative 9.8. And we start here at 5, and we come down to negative, whatever we got, negative 28.5. And let's say this is the final time when it hits. So we're just going to draw a straight line from here down to there. So this is the peak. So it's going up, it reaches the peak, and then it goes down, hits the ground. And because we're just one straight curve, we just have one parabola. So we start off here at 40, and here's the peak. So let's just bring that down. And we'll bring down the final time here. So the peak's going to be right there. It's going to be not that far above 40. So it's pretty flat here. And then it goes, boom, hits the ground. So it's just one continuous parabola. You know, the parabola, you could go back negative time, but that doesn't actually happen, but in terms of a mathematical situation. So this is position versus time, and this is velocity versus time. So that's how the velocity curves go.